Hello everybody. Are you all there? Okay. If anyone has a connection problem, please let us know. I mean, if the sound is not coming well, or if you cannot read the blackboard, please let us know. So, lastly we defined the representation, this concept of representation, right? And also we talked about reducible and irreducible representations. Now, in the previous chapter, we discussed a particular representation, which we call a joint representation, right? So let's first check whether what we call a joint representation, do they satisfy all the properties that we have defined for the representation, right? So the way we define so first of all, again, let me just talk about the representation again. So representation was a map from the Lie algebra V, which is a vector space, together with the commutation relations. So from there, we defined a map which is denoted by R to some n by n matrices. The space is this again a vector space of n by n matrices. Right? I mean, you all know, of course, I didn't mention it, that the space of all n cross n matrices, it forms a vector space, right? Because you can, if suppose M1 and M2 are two n cross n matrices, then clearly any number alpha M1 plus beta M2 is also a n cross n matrix. Right. So it's clearly it's a matrix, there's addition. This addition is a standard matrix addition. So there's a definition of addition in the space of n by n matrices, under which it is a vector space. So this is a map from a vector space to a vector space. Okay. But then, so what it means is that if I have x and y belonging to V, then I have, so x is mapped to Rx, and y is mapped to Ry. Okay. Both are n cross n matrices. But there was one more condition that we had. It was that I mean, this is just one structure. As I said, Lie algebra has one more. There's a vector space structure, and then there's a commutation relation. So what we demanded for the representation in R is not only that the vector space structure is preserved, but also the commutation relation is preserved. So the two conditions was the vector space structure of the Lie algebra V is preserved. So what does it mean? If x plus y is z in the, as I said, there's a vector space structure, so there's a concept of addition in the Lie algebra. So I just take some x and y. X plus y will be again some element of V. Right? So then, this is that's preserved means what? It means that R of x plus R of y must be equal to R of z. Now, what does it mean actually? So this means that, I mean, if I have already defined what is R of X and R of Y, then I cannot just freely choose where the Z is mapped to. I mean, which n by n matrix Z is mapped to. We cannot just choose freely. So it is restricted by this condition. Okay. So, okay, that's one thing. In other words, what this also means is that if, let's say there's a basis, if I choose a basis for the vector space P, let's just call them E1, E2, up to the dimension. So I don't know, let me not use the n here, some other dimension. So let's call it D. So D is the dimension of D. So for example, for SU2, D is 3, right? Because there are 3 independent polynomials, sigma 1, sigma 2, and sigma 3, and anything else can be written as linear combination of the polynomials. So therefore, I mean, I can write any of this x as some coefficients, let's say xi, ei, summed over I, 1 D. Now, if I have defined what is REI for each I, so for all I have defined this. So I just chose two basis vectors here. So basis vectors I call them EI. Okay, and I have defined what is REI. Then that said, that uniquely fixes the definition of R for all the elements, right? Because by linearity property, what we are saying is that R of X is simply xi R of EI sums over I into 1 to D. Right? So this is not a free. And once I fix that, then this is uniquely fixed. So you see that this is a very, this is a very powerful kind of condition. It looks pretty, looks like a very simple condition, but actually what this is saying is that there are only D independent things that you can choose, right? So once I have chosen those D of them, then everything else is fixed. That's right. But there is more to it for the D idea. There is also the commutation relations. So we are saying that this should also be equivalent. So we are saying that so this statement, the second statement here is that under this map, R, the commutation relations CCR. Okay, no, let commutation relations are preserved. Which basically means that if I have x, y belong to E, then, and let's suppose x, y equal to z is going to be some element of E, then what we are saying is that Rx commuted with Ry is equal to Rz. So that is again the statement here. So this means that, this condition already told us that only D of them are independent, right? So once I fix what are the REIs, then I fix everything else, right? But this condition gives further restrictions on even this R of EI. Because, let's say EI and EJ satisfy, these are elements of E, so it's a particular X and Y. Some commutation relation, which let me call it Fijk, EK. Because after all, this is going to be an element of E. So it's going to be whatever it is, I can expand again in the basis. And that coefficient I'm calling that is Fk. But since that coefficient will depend on which I you chose here and which J you chose here, I just use that index to remember that it depends on which I and J I choose. No? So this is just a linear combination. Again, repeated index is summed over. So this condition tells me that REI REJ commutated must be equal to Fijk EK. Okay. So you see that not even all this D, that there are not even independently you can choose D of these different matrices. No? For example, take SU2. If I just impose vector space condition, then I will have choice. I can choose of R of sigma 1, R of sigma 2, R of sigma 3, independently, right? And once I've chosen that, the vector space structure will be there by imposing this condition, right? But when you look at this condition, that's not these three R's, R of sigma 1, R of sigma 2, R of sigma 3, are not independent, right? Because sigma 1 with sigma 2 is some number times sigma 3, right? So once I've defined R of sigma 1 and R of sigma 2, R of sigma 3 is uniquely fixed, right? So there are these two conditions, quite very strong conditions. Okay. Now, let us go back to the adjoint representation. Meaning, we said adjoint representation, but we didn't really check. We didn't really check if it satisfies these conditions. So let's check that. So how we define? But before that. Now, we also mentioned, you see, whenever you have an n cross n matrix, you can think of it as if that these are some operators, linear operators, acting on an n-dimensional vector space, right? Because this n by n matrix, whatever this R of x is, it's an n by n matrix. I mean, there are n columns and n row with various entries here, various numbers. Then I can think of this as acting on a column vector, which is an n-dimensional column vector. So this giving a representation basically is saying that how every element of the Lie data acts on an n-dimensional vector space. Right? So you just define. So maybe I should give it another name. So this was a space of n by n matrix, and this is some n-dimensional vector space. Let's give cook up some name. We're running out of name. Let's say this kind of V, instead of using that. This V is the n-dimensional vector space. It could be, by the way, so far in all of these things, I have not mentioned anything about the coefficients, whether real or complex. It could be either. So if you choose complex coefficients here, then it will be a complex vector space, n-dimensional complex vector space. If these entries are complex numbers, then you call it an n-dimensional complex vector space. If they are real, then you say it's an n-dimensional real vector space. Okay. So we have this space. So what we're saying is that if I take, let's say, some element V belonging to this big V, so this is a particular vector, then this R giving R of x tells you, so R giving R of x acting on V, small v, will be something else, will be again some other, say, W belonging to again capital V, right? So this V could be an arbitrary element of this big V, right? And every time I give you an x, what it does, x takes V to Rx times V. Rx is an n cross n matrix. This is the n cross n matrix times n column vector is again going to be some n column vector. Okay? So therefore, when you give a representation, what it is telling you is that how the Lie algebra is acting on an n-dimensional vector space. This is n-dimensional vector space. So what we are doing is that we are giving a rule. So this is a transformation rule. So given an x, this R of x tells you how it transforms this n-dimensional vector space. The transformation rules. So that's the idea. So now this we can now go to the adjoint representation. We see what's happening. So adjoint representation is just a particular representation, which has what as a property. So first of all, if V is so it is actually taking V to V. In other words, we are taking this capital V to be again V. So this is the capital V. The capital V I take it to be the original vector space itself, the Lie vector space. Okay? It's a special case. Here there is no restriction on this n. and D. There was no, D was, I should write down somewhere. So dimension of D is small. This is what I call small. And this one, dimension of this curly V is N. D and N have nothing to do with each other. A priori, there's no relationship. Okay? But what we are, this adjoint representation is a special case where this curly V is the same as the V algebra itself. Okay? So that's a very special. And it turns out that this representation exists. No matter what V algebra you give me, there is always an adjoint representation. That's always. And the way we defined was the following. So as if I give you x and y, so x belonging to this V and y say belonging to this. Of course, there are two things are the same, but think of this guy as the space on which the transformation is taking place. X is the guy which is transforming, and y, this V is the space on which x is transforming. So y, you think of y as an element of that. Then what if x does? X takes y to add x acting on y, add x, since x is a d-dimensional, this is a d-dimensional vector, clearly this is a d cross d matrix. Why? Because y is also d-dimensional. This is also d-dimensional. So any linear transformation will be again expressible in terms of as a d by matrix. So this is a d by matrix. And again, what is the rule for that? So I want to define how this, what it does. And the definition was simply that this was equal to the commutator of xy. This is a specific thing, and this is a particular representation. It's not the most, it's not a very general representation, it's a particular representation where the action is precisely the commutator. Is there any question on this point? This certainly belongs to V. V, which is in fact in our case is curly V. Okay? So you took an element in the curly V, and after this action, the x, again you get an element which is in curly V. Okay? It's linear because if I take y1 and y2, so if I take this, it's a linear action, because if I take y1 and y2, in V, in curly V, which is equal to V, then add x acting on y1 plus y2 is the same as x of acting on commutator with y1 plus y2 by this definition, and that's the same as xy1 plus x. So it's a linear. So this is the same as add x of y1 plus add x of y2. That's it. So the linearity is a linear action. So therefore, I can write this transformation always as a d by d matrix. In general, the transformation is not linear. You cannot write it as a d by d matrix. But here we have shown that this transformation is acting linearly on this vector space. So therefore, I can express it as a matrix. Second, so this is fine. This is okay. So this is just this linearity is just to check that this action I can write it as a d by d matrix.
Professor, I have a question.
Yeah.
So you said that we are considering a vector space V of dimension D. Do you mean that the number of bases like each I that you considered earlier, the basis of the real algebra?
Yes.
The number of bases is D, or do you mean that we are considering D by D matrices?
D by D matrices, yes. I mean, that's okay. Let me see. So what we said is, so we used, we took the D to be the dimension of the Lie algebra, and we took the D, this curly space to be the same as V. So this is also D-dimensional. So both are D-dimensional. Now, now I define an operation. I define this add of x acting on y is the same as x commutator y. Right? Now, if this action is linear in y, okay, then I can always write this add of x as a d by d matrix. Because why? Because I can always choose a basis for y. Okay. Let's call it E1 and ED. Okay. If I specify, and then what we're saying is V is D-dimensional. Okay. So I can always choose a basis. Let's say EI, a basis, and I can express y as some coefficients. Let's say yi, ei, some to y, and then in this basis I can represent y. I can describe y as a d column vector where the entries are simply y1, y2, up to yn. Yes. So once you choose a basis, you can write as a d column vector. Now, so why is this a matrix? Add x as a matrix, d by d matrix, because by linearity. So suppose I know how add x acts on E1, E2, E3 up to ED, right? Then I know how it acts on this column vector, right? By using the fact that it's a linear action, right? So add y, add x acting on y is the same as sum over yi are just numbers, and add x acting on EI. So once I tell you how this acts on EI, right, then simply this one is fixed, add x is fixed, and you know how, I mean, these coefficients will give you the elements of the matrix, because after all this object is again, now I'm add x acting on EI will be some coefficients. I know, let's call it xi, xj, ej, xij, ej. Right? So again, the notation is that whatever it is going to be a linear combination of the basis vectors. So I can always define in terms of the sum of the basis vectors. Coefficients will be some numbers. Okay. So this j is just the summation index here. So j equal to 1 to p. But I think here, because this is when the add x acts on the EI, right? Of course, if I change the I, these numbers are going to change. Okay. So, and this xij, so now I can write add x as simply a matrix whose entries are x11, x12, x21. So that's all it is. I mean, so once you are given a linear action on a vector space, you can always write that linear action as a matrix. That's simply coming from this here. So because if you plug that in here, in this expression, this just becomes xij, ej, right? So the coefficient of ej is yi, xij, which is exactly what you will get when you multiply this matrix to this entry, this column equation. Now you have to check it whether it's x12 whether it's a transpose of this or not. I mean, you have to just carefully look at it, but you can understand that I can write it as a d by d matrix. This is fine. So far I still have not used anything else. I mean, I have not still checked the computation. So this is just a vector space. Why I think of it as a column? Well, I mean, okay, yeah, x is in the d-dimensional vector space, and y is also in the d-dimensional vector space. But this particular action that I am defining, so I can write this as a d by d matrix. Now, but then, so what about the commutation relations?
So, Professor, in general, the dimension of the matrix shouldn't be need not be the same as the dimension of our vector space of the algebra, right?
Yeah.
In this particular case, we are considering the same dimension.
Exactly.
The matrix.
Precisely. Yeah. I mean, once I finish this, then I will go to construct all the irreducible representations of SU2. But for the time being, I want to relate to the previous discussion, because we never checked that the adjoint of X was a representation according to the definition. So let's just check that. So we want to check. First of all, let's look at the linearity. The vector space, preserves the vector space structure. There are two conditions, right? One, that it preserves the vector space structure. Of the linear algebra. Well, that's easy to see because we have defined add of x. So let's suppose x1 and x2 are two arbitrary elements of. So we want to ask the following question: add of x1 plus x2, is it the same as add x1 plus x2? Okay. This is the question. So there are two arbitrary elements of the vector space B. I have a notion of adding this vectors in the Lie algebra, right? Because Lie algebra is a vector space. So I can just add these two. And then I ask the question, is add of x1 plus x2 the same as that? Well, to do this, I have to just check the action of each of them, the left-hand side and the right-hand side, on an arbitrary vector y. If it is true for all y, then this relation is true, right? So if add, so the question is add of x1 plus x2 acting on y, is it equal to, that's the question, add of x1 acting on y plus add of x2 acting on y. For all y, I mean, it should not be just for some particular y, this should be true for all y. Well, so we can check that. So what is the definition was this, that add was given by the commutator. I mean, the definition of add x acting on some y was simply the commutator of x1. Right? So we just have to use that definition. So left-hand side is the commutator of x1 plus x2 with y. And right-hand side is the sum of two terms, which is this one is the commutator of x1 comma y, and this one is the commutator of x2 comma y. Okay. And this is, you see, this commutator is linear, and there is a sum of two terms, commutator of x1 with y plus commutator of x2 with y. So this is okay. This part is fine. Now let's look at the slightly more non-trivial one, which is that it should, the second condition is that it should preserve the commutator structure. So the second condition was that add x, the question was does the add x, the way you define add x, does it preserve the commutation relation? The Lie commutation relation. Let me just write CR, commutation relation, instead of writing commutation relation. Okay, so what I want to prove this so what I need to prove is that if x1 with x2 is, let's say, something else, x3. Okay. This is the fact that this is reality means that this is defined. The commutator of x1 and x2 will be some element of the V, which I call x3. Okay. So what we need to check is the add of x1 commutator x3, x2, is it the same as add x1, commutator of add x1 with add x2? So this is the question. So this of course, this is the add x2. because x1, x2 by definition is something which I call x3. One element which I call x3. So the question is that is add x3 the same as the commutator of add x1 and x2? So this is all d by dt. So this is the question. So let's just use a definition again, how we have defined add x, and check whether this is true or not. So again, we want to apply this on an arbitrary, this equation on an arbitrary and see if it is true or not. So let's apply the left-hand side. So we want to apply this both the left-hand side, both left-hand side and the right-hand side of the equation on an arbitrary vector. Y in B, right? Because remember the add was acting on the linear itself, right? The vector space on which it was acting was itself. Okay, so we want to check whether add x1 commutator with x2 acting on y is it the same as the commutator of add x1 add x2 acting on y. So this is the question. So let's start from the right hand side. So then this open it up. This open this up. So what is this? This is add x1 add x2 acting on y minus add x2 add x1 acting on y. This is perfectly verified, right? Because add x2, any add acting on y is again an element of the vector space. So I can define again another add action. This is fine, right? This makes sense. So first let's look at that. The left-hand side. So x2 acting on y, add x2 acting on y is simply the commutator x2y. That was the definition of that. And then on this, which is again the element of the vector space, V, I apply add x1. So it's going to be a commutator of that. That's the first term. Second term is minus. And here, the order is changed. First I apply x1, so I get x1 commutator with y. And then I apply x2, so it's going to be a commutator of y. So that's the right hand side. So this is the right hand side of this equation. So let's try to expand it a bit. So this y is x2y minus y x2. And then I have to take the commutator of that. So it's going to be x1 times this minus the other way around. So minus x2y minus y x2 x1. That's the first term. Right? And then the second term will be minus of x2 and then x1 y minus y x1. And then minus plus. So plus x1 y minus y x1 x2. That's what. So now let's see, there should be some cancellations. Is it cancelling? Yeah, for example, let's see this term. Let's call this term 1. x2, y, x1 with a minus sign will cancel with the minus plus, which is x2, y, x1. Right? So this term will cancel with that. Something else to cancel? Let's see. This one, x1, y, x2, x1, y, x2. The same term. This is coming with a minus sign, that's coming with a plus sign. So the term number 2 cancels with this term number 2.
And the first term also get x2, x1y, and the other one x1, x2y.
This one. Sorry, no, this one is okay. This. Is there anything else? Which one you said?
The first one is the left one. First one, x1, x2, y, and then y, x1.
No, this is, I mean, the y is still on the right hand side. Y is, this is a matrix multiplication, you can't move. You can't change. If it was, if you could exchange, this is already zero. So the matrix you have always remember the order. They're all matrices. I mean, for example, take x2. In the this case, all these x1, x2, y, etc. These are all 2 by 2 matrices, right? These are combinations of polymatrices. So the order is very crucial. Okay, so this is all vanished. So finally, what is left over? So left over is, so let's maybe write somewhere else this.
Professor, will you use Jacobian identity?
Yeah, this is Jacobian. Yeah, exactly. This is Jacobian. Yeah. I mean, I'm basically trying to prove this Jacobian identity. Yeah. So this is the first term is x1 equal to y. Okay. That is left over. And then here minus plus x y is to x1. So this is the term which is left over. That's from the second. And then from here you get minus x2 x1 y. And from the last term is minus again minus y x1 x2. Now these two things, you realize it is nothing else but the commutator of x1 with x2 times y, right? These two terms together. Is that? Because this is x1 x2 minus x2, y is always on the right hand side, so there is that. And this one is plus y, minus y, and again the commutator of x1 because you see, minus y, your x1, x2, this is x1, x2 minus x2, x1. So that minus makes it plus plus. So is that, which is the same as the commutator of x1, x2 with y. No? But that's exactly this right hand side, left hand side. Left hand side by definition is whatever this element is. So in this case it is x1, x2. That is commutated with the y. Because the adjoint action is just a commutator of whatever is there, y. So this proves that this is indeed satisfied by it preserves the commutation. This definition preserves it. And what he mentioned, that this is nothing else but the Jacobi identity. The Jacobi identity is this is a Jacobi identity which you might have seen in the matrix algebra. So if I'm just given some x, y, z, and look at this commutator, and two other terms. The two other terms being obtained by just cyclically moving. So let's say z, I move the z there, x there, and y. So there are all. And then there's one more term, because I can again move cyclically the same way. So this becomes y, z. And this goes there, that goes there, that goes there. The statement is this identity is zero. That's a Jacobi identity. This is the general property of matrices. I mean, square matrices. This is always satisfied. And it's just, you prove it just exactly like that. You just open it up and you will see that everything cancels. Okay. So it's crucial that Jacobi identity is behind it. The fact that it's a joint representation is in fact, the way we define a joint representation is a true representation. That it preserves both the. Later on when we discuss, at the moment we are always discussing like SU2 and we'll discuss SU3, which are all given in terms of matrices. But after that, when we start discussing more general structure of the algebras, we will have that Jacobi identity condition also inside the definition of Lie. Because here the algebras were realized as matrices, but perhaps there are some symmetries which you don't realize explicitly as a matrix. In some other way you realize. Then you have a notion of a commutator, but that commutator is not, you cannot write it as a matrix commutator. If you could write it as a matrix commutator, Jacobi identity is automatic. There's nothing more to impose. But if you do not have a matrix realization of it, then you have to put in this extra condition, the Jacobi. So the Lie algebra is defined together with that Jacobi condition. It's not just the commutator, not just any commutator. The commutator must satisfy the conditions. Okay, that's it. Now, in the remaining time, what I will do is, so this says that a joint representation is a particular representation. It is a representation, but of course it's a particular representation. For SU2, it has a dimension the same as the dimension of the Lie. So in particular for SU2, dimension is 3-dimensional representation. If you take SO3 again is dimension 3, so a joint representation is again dimension 3. And in fact, I think 2 lectures ago we showed that that representation was the same. The representation of the SU2, a joint representation of SU2 was the same as a joint representation of the SO3. Okay, now our aim now is to construct all the irreducible representations of SU2. Because as we discussed also before yesterday, that if you know irreducible representations, then you know everything, because you just have to put them together to get a reducible representation. Right? So the main question is to know the irreducible representation. Irreducible representations. But is there any question on that definition, irreducible and reducible? Or was it clear to you?
Maybe asking foolish question. Does the second condition imply that the first one is already satisfied? I know it's not. Does the second condition imply that the first one is already preserved? I know it's not.
Which is the first condition?
The second condition or preserving the commutation relation.
Yeah.
The first condition is preserving the same vector space.
Yeah. So that is automatically satisfied because in the definition of the algebra, we will demand that whatever the commutation relation you have defined on the algebra, right? Because the algebra comes with a commutation relation, right? That commutation relation must satisfy the Jacobi. So this is a condition, extra condition. On the abstract definition of the algebra, you have the extra condition. But here we didn't say it because our algebra is also realized in terms of matrices. SU2 in terms of polymatrices. No? So for the matrices is an identity. The Jacobi identity is not something that we need to put in by hand. So it's all right. Yeah, the abstract definition of the Lie algebra, you don't think of the Lie algebra as given by some matrices. In this course, we'll be always restricted to, we'll be always talking about the matrix groups, and therefore matrix algebra. So the definition of the algebra itself involves matrices. So in that case, you don't need to put that Jacobi algebra definition. It's automatic. Because the reason why I'm talking only about the matrix algebra is because that's what has appeared in the part of our course. That's what we need for the rest of the course. Okay. So now our aim is to construct all irreducible representations of SU2. So this again, now the procedure will be very, this procedure, all that I'm doing for SU2, you will see that the same procedure will work for SU3 and in fact all the ideas. So please pay attention to this. It's very simple, very easy, but if you understood this very well, then the remaining discussion on SU3, SU4, we'll be discussing in detail SU3 in particular, it will become much easier. So this is the so remember for SU2 we have these three So sigma I. So there's a sigma 1, sigma 2, and sigma 3. This was the three body matrices. These were the generators, the basis for the generators. I could choose them as the basis for the generators. Basis for the D algebra. Okay. Now, notice that, of course, these are Hermitian matrices. So, I mean, in some representation R, you'll have R of sigma 1, R of sigma 2, and R of sigma 3. And once you define these guys, then everything else is written because of vector space structure. And as we said, that even this is not freely, you cannot choose freely these three matrices, because the commutator of this sigma 1, sigma 2 gives you sigma 3, right? Or I sigma 3. So there is a restriction of that. This is not something independent. Once you specify these. Now to study this, and in particular, we can ask, so this is acting on some, so let's suppose this is some n cross n. Yeah, okay, let's call it. And I think here okay, some notation. So n cross n matrices, so you can think of it as acting on n dimensions, n dimensional matrix space. Column vector. Now, one question you can ask is, one would like to ask, as one possible question you can ask is, what are the eigenvalues of this? This will be some matrix. What are the eigenvalues of this matrix? Because if I know the eigenvalues of this matrix, then I know that at each of these states, okay, what quantum numbers are cast, what are the eigenvalues? So that's a natural question to ask. So for this reason, it is. I mean, we would like to use the Hermitian matrices. That's why I didn't put the I. Okay. Because for Hermitian matrices, Hermitian operators, the eigenvalues are really. No? So for this reason, we don't put the I. But although also you can discuss it with the approach, it just becomes easy. If you put I there and then in front of the eigenvalues will be pure imaginary. So you'll have to put I there. But this is more. The second thing you notice is that these guys don't commute. So in particular, since they don't commute, also this commutator R sigma 1, R sigma 2 is not equal to 0. Is not equal to 0. In fact, it is equal to R sigma 3. Right? So these three matrices are not mutually commutative. So you cannot diagonalize all of them. You cannot find simultaneous eigenvalues for all of these three matrices. Right? I mean, you can find simultaneous eigenvalues for two matrices only if those two matrices commute. Otherwise, you cannot find. That is the reason why, as you saw in the Hadamard problem or spherical harmonic oscillator, that you could only define, say, J3 quantum, third direction. Then J1 and J2 you cannot define. You can define the total angular momentum, J square, right? And you can choose only J3 or J1, one. You can only choose one. And find the eigenvalues. But then you cannot define the angular momentum in other two directions. Right? It's precisely for this reason. Because only one, these guys, sigma 1 and sigma 2, do not commute with sigma 3. So if I diagonalize this matrix by choosing finding eigenvalues, no? And choose, if I find eigenvalues of this operator, this matrix, then what I can do is I can choose the basis to be those eigenfunctions. Right? In that case, this becomes diagonal. No? But then these are not diagonal. So it is not very convenient to use this. Okay. So what is more convenient is to think of this. So I want to look at the computation relation. I want to find some combination, let's say x sigma 1 plus y sigma 2, such that the right hand side, again, sigma 3 with sigma 1 is going to be I sigma 2 or plus or minus I sigma 2. And sigma 3 with sigma 2 is going to be plus or minus I sigma 1. No? So whatever it is, right hand side is going to be again some combination of sigma 1 and sigma 2. No? But what I want is I want this to be the same combination. X sigma 1 plus y sigma 2. And you'll see why this I mean, once you find that, why it becomes much easier to construct representation in a different way. So you can see, you can show that actually this combination I can choose to be what I call sigma plus and sigma minus. Sigma plus and sigma minus. And sigma plus minus are, say, sigma 1 plus minus so let's just work it out. So I take the first one, the plus sign, or actually I can put both of them. Sigma 1 plus minus and sigma 2. So what is this? Sigma 3 with sigma 1 is I epsilon 3 1 2 sigma 2. Right? And this sigma 3, so there's already a plus minus I here. Then sigma 3 with sigma 2 commutator is I times epsilon 3 2 1 sigma 1. Right? That was remember sigma I sigma j was I epsilon I j 2I. So maybe I should choose half. Okay, you can divide by half or something later. So there is a 2I and a half of 2I. This was 2I. Okay. So let's now epsilon 3 1 2 is the same as plus 1 because it's equal. I mean, you can move this 3 2 times here. I mean, epsilon we have defined epsilon 1 2 3. Epsilon 1 2 3 is plus 1, and any exchange that will give you an extra minus. So you can go from here to there by 2 exchanges. First you exchange 3 1, and then from there you exchange again 3 2. So 2 exchanges. So this doesn't change the sign. Whereas here, you see, you need to first of all move the 1 here. That is 2 steps, so that doesn't change the sign. But then I have to change again to 3. Right? So there are three exchanges. So that means this is a minus. So you get let's say so you get here I times I is minus plus. So you get here plus minus 2 sigma 1, and here you get 2. So this is plus 2I. That's 2I sigma 2, which I can write as plus minus 2. I take out common factor sigma 1, and then 2I. There's a 2I. 2I. And here I square is 1. So this is 2I. There's a 2I. Sorry, I made a mistake. Let's go again. This is plus 1. So this term is plus. This term is plus. 2. What is it? No, sorry. So let's look at this term here. This is minus. I square is minus plus. So this was correct. Plus minus sigma 1. Okay. 2 sigma 1. Sorry, 2 sigma 1. And here we have plus 2I. So if I now take out plus minus 2, so I will get here sigma 1 and plus minus I sigma 2. Okay. Which is the same as, so here this was sigma, so let's write down the commutator of sigma 3 with sigma plus minus, right? These two signs correspond to sigma plus minus is equal to plus minus 2 times sigma plus minus. And in order to get rid of this 2, let's redefine. So I put here sigma 3, so sigma 3 by 2 and sigma plus minus by 2. So this is that. So let us divide by everything by 2. All the sigma matrices by 2. That 2 you divide just to get rid of that 2. This we did already. Remember, it was sigma by 2 which was related to the SO3 generators. Sigma A by 2 or I sigma A by 2 was related to J. Okay. So I don't put I because I want sigma 3 to be Hermitian. Okay, that's why I removed the I there. So we have this relation. Okay. Now let me just call. So let me just give a name to it. The same notation. Yeah. The names given. Yeah. So the name we have this could be called, we are calling this this is just for convenience. It's not that anything is changing by going this way. But with this choice, we'll be able to construct all the representations. So the generator, I will call these generators H as sigma 3 by 5 and E plus minus. I will call this plus minus. I will call sigma plus minus. That's just so to compare it with the notation in the notes. So the notes, that's why it was defined. So the commutation relations are, so that commutation relation is simply H, E plus minus, is equal to plus minus E plus minus. Now you can also ask the question, what happens if I look at the commutator of, this was for sigma 3, but I can also ask the question, what happens if I look at the commutator of E plus with E minus? Right, that's another thing we can ask. So we can just plug that in here. So what is E plus? E plus is nothing else but sigma 1 plus I sigma 2 divided by 5. And this one was sigma 1 minus I sigma 2 by 2. Actually, I'm not sure if okay, let's see. So what is this? Let's look at that. So sigma 1 plus sigma 1 is 0. So we have sigma 1 with I sigma 2. So 1/4. Okay. 1/4 is from here. I minus I. And sigma 1 sigma 2 is 2I sigma 3. And the second term, second non-zero term is when you look at the commutator. Sigma 2 with sigma 2 vanishes. So we have sigma 2 and sigma 1. This is only the commutator which is left over. So you get here I over 4. And then sigma 2 sigma 1 is minus I minus 2I sigma 3. Now if you add that up, you find it is sigma 3. So the convention, yeah, that's right, sigma 3, which is the same as 2H, because H was sigma 3 by 2. So the commutation relation is equal to H. So this is the same thing that this is the SU2 algebra, except that I have chosen some different basis. Okay. Instead of sigma 2, sigma 3, I have chosen this basis to be sigma 2 plus minus I. Sigma 1 and sigma 2. I chose it. Okay. Then it just turns out to be more content. That's all. It's the same, content is the same. Information is the same. I just chose a different basis. So this is in this language the computation relation. Now why did we do this? The reason is the following. This should remind you of something. You must have seen in quantum mechanics. This raising and lowering operators. No? The sigma plus and sigma minus are the raising and lowering operators. The way to see this is that, let's suppose that, as we said, sigma 3 is the Hermitian object. So that means H is Hermitian. I should be able to always have that. No? Which means I can find eigenfunctions and eigenvalues. So let's suppose I found, so this is all in some representation R. So let's say I found RH acting on some vector B. And let me use the same notation again for this. Okay, here something is called V here. So some vector B is some eigenvalue. Let's just call it N V. There is some eigenfunction with the eigenvalue. I mean, at the moment, I can even let me call it X because I don't know what the value is. X could be any real number because this is Hermitian. So the eigenvalues are real numbers. Okay. So we look at this. Okay, this is fine. Now you ask the question, what if I apply E plus on B or E minus on B? So if I apply E plus on B, so R E plus on B, you can ask now, this again another space. This is, I started with one vector in the vector space. So this is in some vector space B, which is some dimension. It's not the adjoint, it's not the Lie algebra, it's some other vector space. Some n-dimensional vector space. We don't know what this n is yet, n-dimensional. So this will be again some, if this is a representation, that means when I apply any Lie algebra, any R of any Lie algebra element on B, it is again going to give me something inside the space. Right? So it's going to be in that space. Now the next question you want to ask is does it happen to be again an eigenfunction of RH or not? In general, you would expect that, right? In general, if you multiply, if it starts with some eigenfunction of a matrix, and then you multiply that eigenfunction with some matrix, some other matrix, it need not be again an eigenfunction of R of H, right? There's no, a priori there's no reason for that. However, this commutation relation is what's going to help us, this particular commutation relation. So if I want to check, so we are asking is this an eigenfunction of RH? That is the question. And if so, what is its eigenvalue? To answer this question, of course, you just have to apply that and check what happens, right? Apply the RH. So let's apply RH on that. Okay. And let's write it in the form of the commutator. Okay. So what I will do is I will write it as RH commutated with RT plus. Actually, let me put here both of the same sign. So I can apply RE plus or RE minus, right? So there are two different states. But I can, by putting these two sides, I can discuss both these states at the same time, in same equations. No? So I just put that, so RE plus minus here, RE plus minus. Acting on B. By acting, of course, you know what I mean. This is n-dimensional. In this representation, these are all n by n matrices. So it is a matrix applied on V. So this is n by n plus n by n. That is n column water. This, but this is not. The original thing was not this commutator. What was this commutator? Commutator has one term which is that, and the other term is the minus R E plus minus R H. Right. So I need to add that term here. R E plus minus R H. Right? Now it is okay, right? Because this is RH, RE plus minus, minus RE plus minus RH, but that minus term cancels with that. So this is the side nothing. The two sides are equal. Okay. Now we use this commutation relation. Remember, the representation has to preserve the commutation relation. Right? So what that means is that RH with RE plus minus commutated must be plus minus RE plus minus. Right? This is just the requirement that the representation preserves the commutation relation. Okay. And furthermore, we have this relation E plus E minus commutated is 2 times RH. So this is what we know, what we deduce from the property, the definition of the representation. Okay. So now let's see that we can try to simplify this. So first term, we use this relation, the commutator relation. So we have, so the first term, this guy and going to here. So the first term is simply plus minus E plus minus acting on B. And the second term is RE plus minus. And then RH acting on B, but RH acting on B, we said this is an eigenfunction of RH with eigenvalue x. Right? So that RH acting on B is nothing else but x times P. X is a number. So I can take that out here. I mean, this is a matrix, but that x is a number. I'll put it out. So this whole thing becomes x plus minus 1 E plus minus B. So you see, RH acting on this vector, this is again an column vector, this is a particular column vector, is again the same column vector times this number. So the answer to this question is yes, it is. So this answer is yes. They are both RE plus minus, RE plus acting on B and RE minus acting on B are eigenfunctions of RH. That's the first thing. And second, the eigenvalues are x plus minus 1. These are eigenvectors. For the RE plus, the eigenvalue is x plus 1, and for the RE minus acting on B, eigenvalue is x plus 1. So the reason why we looked for such combinations, such that x conjugated with that combination is again back the same combination times some number, was for this purpose. So every time I apply RE plus or RE minus, what is happening? If you apply on an eigenfunction of RH, you again get an eigenfunction, but its eigenvalue gets shifted by unit of 1, plus or minus, depending on whether you apply E plus or E minus. For this reason, E plus and E minus are called raising and lowering operators. Raising and lowering. One of them increases the eigenvalue of the H, and the other one decreases the eigenvalue in units of 1. It's not arbitrary changes, it's units of 1. So that's the very important part. Okay. So now, is there any question? Let me just stop here. This is very important point here. We will see that we do the same thing for every HEP and so on with similar techniques. So, any question? Yeah. All right. Now, so let me erase some parts of it. Maybe this algebra is write it here. So the algebra was RH E plus minus. Commutator is plus minus E plus minus, and E plus E minus is 2 RH. There's also remember this H is sigma 3C2. And E plus minus sigma 1. Okay, now what we do is, so I start from this vector. Okay. Now first I apply RE plus. So let's look at that. This has eigenvalue x, right? Under this has eigenvalues with RH. This was the eigenfunction with the eigenvalue x of RH. Now let's go apply once more on this. So this is x plus once more. So RE plus square acting on is again going to be x plus 2. And so on. RE plus to the k acting on B will have eigenfunction x plus eigenvalue x plus k, and so on. Now, you know that if there are two states with different eigenvalues, they are linearly independent. So two vectors with different eigenvalues are linearly independent, because otherwise, no. This you must have seen it in the linear algebra course, right? So that means these vectors are linearly independent. But our dimensionality of the space was some finite dimension, n. So we are looking at some n is finite. N is the finite dimension. So the space on this representation is n cross n matrices. I mean, this representation will be n by n matrix, which will act on an n-dimensional vector space, and that n I'm taking it to be finite, not infinite. If it is finite, then this procedure cannot go on, because all of them, for any k, we are all getting linearly independent vectors. In an n-dimensional space, the maximum number of linearly independent vectors will be n. No, cannot be more than that. So this process must stop somewhere. So how can it stop? It can only stop if at some point, when I apply one more, for some value of k, when I apply one more RE plus on this, you get this state becomes 0. That is the only way this process will stop. If it was not 0, you're going to get something with the eigenvalue x plus k plus 1. So the only way it can stop is that in this chain, this chain of states that I get, at some point, if I further apply RE plus, it annihilates it. Okay? That's the only way it can stop. And we know it has to stop because n is finite dimension. I mean, this V is finite dimension. So it has to stop. So there exists, so this means there exists, so finiteness of n implies that there exists a k such that RE plus to the kb is not 0. It has an eigenvalue s plus k. But when I apply one more R plus on that state, it vanishes. So such a state is called highest weight state. So which means it has the highest eigenvalue. Because this is all plus 1, plus 2, going in the positive direction. Right? So such a state equals to the k v is called highest weight state. Okay, this terminology will become more clear. At the moment, just think of weight as an eigenvalue. This will become more clear when we go to SU3. Okay. So for the moment, we just take it as just terminology. Okay. So, and of course, yeah, so this I will erase this part. So this is the highest state. So what we see is that no matter from where you start, at the end, and start looking at this chain, I keep applying the raising operator. This is the raising operator because it's increasing. RE plus is the raising operator. RE minus is a lowering operator because that decreases the eigenvalue by 1. So here I'm just applying the raising operators until you hit the point where at some stage where after that if I apply again the raising operator, it vanishes. So the definition of the highest weight state, so what is the definition of highest weight state? Highest weight state, I'll just abbreviate it. HW as a highest weight state is that when RE plus acts on the highest weight state, it exists. So RE plus annihilates the highest weight state. It annihilates. Okay, so now let us just start from this highest weight state. Call this particular state, give it a name to it. Okay, so let's call. Actually, yeah, this is something I could have simplified the notation very much. Let me just simplify the notation. So instead of writing all the time with R or bracket, in the notes we have used a notation. By the way, these notes are written by one of my colleagues called Professor George Thompson. who used to teach this course a few years back. So he had prepared his lecture notes, and I find it very logically kind of going very well. I mean, systematically. So I'm just using his lecture notes. So R of the notation, R of H is used by one calls it a capital H, and R of E plus minus is just denoted this is the notation E plus minus. Okay. So this is just to not write this R continuously. So these are our matrices. I mean, these are all n by matrices. So the highest weight, the definition of that is, so highest weight state is something which is annihilated by E plus. R E plus is the same as this. Capital E plus. Yeah, that's it. Okay, so let's start from this. Now the name, what notation? So so we just call this state as phi prime. Give it a name phi prime. So phi prime is the highest weight state. I'm just trying to lead to the notation in these notes. So this was the highest weight state, and just give it a name, phi prime. So phi prime has a property that phi prime, it has what is the property? Phi prime acting on H acting on phi prime, it has some eigenvalue. Okay, if I started from x, it was x plus k in this way, right? But just call x plus k as some j. I just give it a name j. And so this highest weight state, phi prime, satisfies these two conditions. One, it is an eigenfunction of H with some eigenvalue J, and E plus acting on phi prime is equal to 0. So this defines the highest weight state. And we know from this argument that if I'm talking about the finite dimensional space, then there has to be a highest weight state, at least one highest weight state. No? Because from this procedure, we see that there is no way it has to add something.
But in Hilbert space, this relation is plural.
Hilbert space? No, we are not talking about Hilbert space. We are just talking about finite dimension. We are only looking into finite dimensional space. Hilbert space, you are thinking of the quantum mechanics, right? No, that is different matter, because all these things that we will be doing are some internal symmetries of the particles. No? Internal symmetries, which is called color degrees of freedom or isostanes and things like that. So those are always finite dimension. When we talk about Hilbert space, because then the fields themselves will be building on the space-time. So they will be functions of x1, x2, x3, and the time. No? So Hilbert space is that, but this is all happening in internal space. So this is
this can't be generalized like infinite dimensional.
sorry, repeat it.
This right now we're working finite dimensional space, but this can be generalized like infinite dimensional space.
Infinite dimensional spaces, there could be some technical problems. Of course, you can take any of these representations and take tensor products or sounds of this representation infinite number of times. So you'll get that. Yeah, I don't know if you directly want to talk about infinite dimensional representations, there could be some problems. In fact, it turns out that, I mean, you remember that we discussed about the U1 and or U1 or SO2 and SO11. We talked about that, right? So SO2 preserved the length on a Euclidean plane, right? SO1, was the Lorentz transformation. Okay, in a plane where say one of them was the x coordinate, another was the time. Okay. Now this group is non-compact. Okay. So it turns out that all the representations of this are infinite dimensional. They don't have finite dimensional representations. But for the compact groups, which is what we will in particle physics are realized as internal symmetry groups. Internal symmetry groups, all these compact groups. So compact groups always finite dimensional representations. You can have unitary representations, which are finite dimensional. Whereas for the non-compact, you don't have any unitary representation, which is finite dimensional. So I will be talking always about the finite dimension. Okay, so now this is fine. Still, we are far from really characterizing the representation. All we have learned is that there is a highest weight state. At least one highest weight state. So that's and we define it. So now, since I know that such a state exists in any representation, so let us start from that. And I apply all the generators of the Lie algebra. Basically, just these three: H and E plus minus. I already know E plus how it acts. E plus annihilates it, and I also know how H acts on it. H gives you eigenvalue J. So the only other thing I can apply is E minus. Okay. So let us start with C prime and start applying E minus. So this was start with C prime. Now I apply E minus on C prime. Okay. And what is it going to do? It is going to, if J was the eigenvalue of H for C prime, then this will have eigenvalue. So this is the H eigenvalue. So here we started with J is eigenvalue. Then this is a lowering operator. Remember, it's a lowering operator. So it will have eigenvalue J minus 1 and apply E minus square on 3 prime. This will have eigenvalue J minus 2 and so on. If I apply, say, some L, let's say L times, I will get J minus L. Again, from finiteness argument, this process has to stop somewhere. Right? It cannot go on, because if it goes on, it's infinite dimensional. Because these are all linearly independent states. Right? So there should be, so finiteness again implies that there exists an L such that E minus to the L, E minus to the L P prime is not 0, but E minus to the L plus 1 active on 5 prime is 0. That's only where it can stop. Right? Okay. So this is so you see that we have when I apply E minus on these states, this state goes here, this state goes there. So E minus takes you this way, one step at a time. When you apply E minus, you go from here to there, from here to there, from here to there, and from the previous one there. But the next one, when I apply it, it gives you 0, identically 0. So therefore, the dimension of the space is L plus 1. I mean, there are L plus 1 independent, linearly independent values. That's the first statement. The second question you can ask is, now, this L plus 1 dimensional space, does it give a representation of the Lie algebra? So we already know that the E minus action just takes me from here to there, from there to there. So E minus is perfectly well defined in space. Right? H is also well defined because each of them are eigenstates. So H acting on the state gives you back the same state. Right? So this is also well defined. So the question we want to ask is, if I apply E plus on this, on any one of them, do I get back again one of these states or variation of these states? Right? If I get a new state when I apply E plus, then this is not you need to add more states, right, to get a representation. Right? So let's see what happens if I apply any. If I apply E plus on any of these states. So let's say E minus to the K, let's say K, theta, where K is between 0 and L. So K is between 0 and L. Because that's all the states we have here. So let's see what happens. What is this? Well, first of all, if K equal to 0, this is E plus T prime. But by assumption, I erase that. The phi prime was the highest wave state. This was the highest wave state. So it satisfies the condition that E plus phi prime is 0. So when k is 0, this just gives you 0. So nothing to check. So what we want to check is for the remaining guys. For k equal to 1, so k greater than 0, so k equal to 1 up to 2. I mean, k equal to 0 is trivial that this just gives you a 0. It doesn't give you some new state. We are asking the question, does it give you some state just outside this list of states? So let's take any of these cases and let's start again, do the same thing. This is standard. The way we arrived at the conclusion that E plus and E minus was a raising and lowering operator, what we did, we applied E plus on say some state. Then I looked at the H acting on that, then wrote it as a commutator and removed the extra piece which is involved in the commutator. Right? And then we deduce a lot of conclusions from that. So we do the same thing again here. So let's write it like E plus and E minus, then E minus to K minus 1. This chalk is going in. So phi prime. So K. So I can write that. But then there is this E plus E minus minus E minus E plus. So I need to remove that extra piece. So that when I remove the extra piece, that gives me plus E minus E plus E minus K minus 1 phi prime. But this guy is what? This guy is from this commutation relation. You see, E plus E minus commutator is 2H, 2 capital H. Right? So this is the same as 2 capital H. But capital H acting on this guy, this is nothing else but that state. I mean, it's one of these states with the K minus 1. Which the eigenvalue will be, so this acting on this state, so simply gives you 2 because of that, and J minus K minus 1. Right? Times the same guy. Okay. So this state is fine. This state already existed in this list. Right? Is now some number times one of these states. But about this we still don't know. So what we do again? Start pushing. So what is the idea? We are trying to push E plus step by step. So this is the idea. Step by step. So we did this first step. Now what we are left with is E plus here in this position. You again write this guy as E minus to the K minus 2 times E minus. Right? And use the commutator here. So, and then there will be an extra piece where E plus moves one more step here. Right? So let's just do one more step. So what we get here? This time I write it like this. So I get here E minus. And then, so there is a term which is simply the commutator E plus E minus. Then we have the E minus to the K minus 2 phi prime. But then I have to remove the extra piece from here. When I wrote this thing as a commutator, I need to remove that. So that is plus E minus E plus, so E minus square. E plus E minus K minus 2 phi prime. This one again is 2H. But now H is acting on this state, which is an eigenstate of H. Right? So it's going to be, what is the eigenvalue? It is J minus K minus 2. Right? So this term will give me plus 2 J minus K minus 2. And then there is a number now, I take it out, so it's again E minus to the K minus 1. There is a K minus 2 here and there is 1. It gives you E minus to the K minus 1. phi prime. So this is gone now. Okay. But now what has happened? E plus has moved. So you see, this is what we are doing now. We are moving step by step E plus in. Closer and closer to phi prime. Why are we doing that? Because I know if I can move E plus all the way there, then E plus acting on phi prime is 0. So you keep repeating these steps, I don't know, k minus 1 steps or something, or k steps. At the end, what you will get is the term where all the e minus to the k will be on this side and e plus will be active with phi prime. And then I use this equation. That's 0. Right? So you keep repeating this step by step. So step by repeat the steps. Until E plus directly acts on phi prime. In this case, it is 0. There's no E minuses inside, in between. All the E minuses have been moved to the left, and E plus is also there. So that will be 0. And then every state will be proportional to E minus to the k minus 1 phi prime with some numbers. So in fact, you can compute what the numbers will be. So it will be. So you see, in every step, this k initially was k minus 1. Next time is k minus 2. Next time it will be k minus 3. Right? Because next time when I move again, this thing. So again, you write this as E minus times E minus to the k minus 3. And then again, write this as a commutator term and move the extra PCB E plus X in here. Right? So every time you will keep reducing the numbers. I mean, the commutator term gives you H acting on that, whose eigenvalue will be J minus K minus 3. Right? So you will get this expression, the final answer will be 2 times J minus K minus J minus K minus let's call it X, okay, times E minus to the power of K minus 1 phi prime. And there's a summation here, and summation starts from the first term is S equal to 1. And the last term will be when it just acts on the, so it will be just J equal to K, right? I mean, the last term would be when the commutator acts directly. So there is E plus E minus acts on the state phi prime itself, right? And everything, all the E minus powers are on the left. This step, you keep repeating, and the last step, you will have this plus, so there will be like E minus to K minus 2, and then here, K minus 1, K minus 1, and there will be this term plus the term which will be E minus E plus phi prime. This term is 0 because it is the highest weight state. And this term is going to give me 2h, but that h eigenvalue will be simply the eigenvalue of phi prime, which is j. Okay? So the last term should be just 2j, which means s equal to k. So the range is s equal to 2. Okay? But anyway, this itself, okay, it's something. But whatever it is, this is some number. Okay? Times the state. So what we are saying is that if I apply E plus on any one of them, so what I did, I applied E plus on E minus to the k phi prime. The result is some number times E minus to the k minus 1. So E plus is just taking you a state from any one of these states and moving it one step up. It is not giving you a new state, not giving you a linear determinant. It's giving you some number times the state which already existed. So just like E minus takes you one step down every time you apply E minus along this direction, E plus takes you one step up. So that's so therefore this set of states provide a representation of the full algebra, right? Because E minus it takes a state here and brings it back again. E plus also, and H obviously because these are all eigenfunctions. So this is an introduced representation. This is the space is closed under the action of E plus, E minus, so in other words, sigma 1, sigma 2, sigma 3, because this E plus and etc. are linear combinations of sigma 1, sigma 2, sigma 3. And therefore, the full EI, because sigma 1, sigma 2 are bases. So we have constructed a representation, irreducible representation, in fact, of dimensionality. What is the dimensionality? It is to the power of, so L plus 1 dimension, right? Because we started with E prime and all the way up to E minus to the power of L. So this is an L plus 1 dimensional representation. This number is also an important number, so I will not erase that. So this was the conclusion. This was we said it's E plus acting on E minus to the K P prime was equal to that. Now, so this space. So we have now L plus 1 dimensional space. L plus 1 dimensional space. And I can choose the basis as the basis are P prime, E minus P prime, all the way up to E minus to the L. So these are L plus 1 state L plus 1 vectors, and this are all linearly independent because they all have different eigenvalues. With respect to it, they are clearly linearly independent. So this defines L plus 1 dimensional space, and this space is irreducible representation. So that's that. It is an irreducible. Okay, but still there are several unknown quantities. There's one is this L and other is J. J was something special, right? J was the eigenvalue of the highest weight. H acting on P prime was equal to J. So the question you can ask now is there a relation between J and L? That's one question. And second question is that is there any restriction on J? Well, L has to be integer because clearly I am doing L steps. So L is this is surely an integer. But J could be any real number. Right? All we are saying is this is an eigenvalue of a Hermitian operator. So it has to be real, but it could be any real number. It doesn't have to be integer or half integer or something. Right? The question is, can we come to some conclusion? Now, the statement is the following. Now, if you have, so therefore, I mean, in this space, you have E plus, E minus, and H. These are all L plus 1 cross L plus 1 matrices. Right? So let's do the following. So these are because these are all defined. And we said that was the purpose of proving, purpose of checking this. That when I apply E plus, I don't get some new state. I get back the same states. So they are all. Yeah.
I have a question.
Yeah.
So we have proved that when we add E plus on this test E minus to the X phi prime, we get one of the states of the states we already have.
Yeah.
So I have a question: why is it necessary to prove that? Because E minus to the K phi prime is already we know that it is one of the eigenstates of H. And we already had proved that when we apply E plus acting on some eigenstate of H, which we call B, and then we found out that it just increases the eigenvalue by +1.
Yeah.
So,
Good question. The point is, suppose, so you are right. I mean, if I apply, for example, E plus on this state, surely I'm going to get something which is an eigenvalue j minus L minus j minus bracket L minus 1, right? But how do I know it's the same state? It may be a degenerate state, another state, you know? You see, so it could happen, right? I mean, there is no guarantee to begin with, right? So the purpose of this was to prove that state that you will get is actually just this state, not some different state. There could be, in principle, see, a priori, there could be some state which has the same eigenvalue. Eigenvalue is clearly it has to be that, if I apply E plus on this, right? But it may be linearly independent state. So that's the property. So this is why we have to prove that it's the gain of the form E minus to some power of phi prime, no? And not something different. Yeah, that's very important because it's not true in general. I mean, this is a particular. This is in SU2 is a special case where there is no degeneracy. I mean, if I fix an eigenvalue, there is also a unique state in a given irreducible representation. When we go to SU3, this will not be the case. You will find the same eigenvalues, but two different states. So, yeah, that is a good question. So, this was a good question. So, okay. So, now how can we find some relation? So, is there a relation between J and L? J and L? Right. Okay, if there is some relation, you can imagine there could be some quantization condition for J, because L is an integer. No? And so the next thing was what are there discrete values of J? Are there, I mean, is there some quantization condition? For J. So there are several ways of doing it. One way to do this, which is I think given in this, that yeah, I mean, if you, okay, I'm not sure if this formula is correct. You should check. I might have missed the range s equal to 1 to k. It could be s equal to 1 to k minus 1, but I mean in the notes it should be the correct one. But you see, this relation I can use. Because I know that I'm saying that E minus to the L plus 1 phi prime is 0. Right? So suppose I just apply this. So I just apply E plus on E minus to the L plus 1 phi prime. Well, this is 0 because this itself is 0. Right? I mean, we said that was just like phi prime is the highest weight state, this is the lowest weight state. Because E minus on I have set. When I apply E minus on that, then I have set. So since this is 0, anything acting on 0 is 0. Any matrix multiplying a 0 state is 0, right? So this is going to be 0. Okay. But on the other hand, I mean, I can still go through this exercise of pushing this E plus step by step in. No? This is how we got that. Then we would say that this is the same as 2. Just replace k. I mean, just write k equal to L plus 1. That's all one has to do. So 2 j minus k plus 1 minus s going from so k. So k is L plus 1. So s going from 1 to L plus 1. We just took k to be L plus 1. This activity I multiplied by E minus to the power of k minus 1. K is L plus 1. So minus 1 means L. P prime. But this state is not 0. You see? Huh? So this is a kind of consistency check. We are declaring that this is a lowest state. We declare that. But then that means this is 0. Okay. On the other hand, formally, whether I don't know, suppose I didn't know this was 0, I apply E plus on that, I am going to get to this state. that state with this particular number. Okay. But on the other hand, if you say this is the lowest state, that this is 0, so left hand side is 0. So that means this sum, I mean, this is certainly not 0, this state is not 0. So the only way this can be 0 is that if this number which is multiplying that state is 0. Okay. So that's one condition. I don't know if this is the same. I'm just passing by that I made some mistake, algebraic mistake in this process. Let me just see if this number is the same. So the number here is, let me see the number. This is, I'm looking at the formula, 6.37. Yeah, 6.37. I mean, 6.36. So there the number, but we have to check whether can we raise here. So the number here is 6.37. 36. Okay, what one gets is sum over R. So since I'm calling S, okay, let me write this R. 2 times J minus L plus R. And then the range goes from R equal to 0 to L. Okay, here the range is going from S equal to 1 to S equal to 1 to L plus 1. So let's call R equal to S minus 1. Right? If I replace R, or in other words, S equal to R plus 1. So write S equal to R plus 1. Then do I get the same as that? Times the expression. Let's check that. If S equal to R plus 1, no, maybe it's not there. Maybe. No, what is the issue here? We said K is equal to L, right? No, K is equal to L plus 1. I didn't substitute that. It's L plus 1. Sorry, L plus 1. I didn't substitute. This was the general expression, but then we just put K equal to L plus 1. So that's K equal to L plus 1. But here I didn't change K. So this K is L plus 1. Okay, now it's not correct. Because when you put S equal to R plus 1, so this is R minus R minus 1, minus 1 cancels as plus 1, which is the same expression plan, right? J minus L plus R. This minus becomes minus becomes plus. That's the expression, the range. Range is equal to the range. If here we're saying S equal to 1. If S equal to 1, clearly R equal to 0. So that is that lower limit. And here we said S equal to N plus 1, but then R is equal to N. So this is the same. This is the same. So I didn't make some. It's very easy to make some silly mistake when you're looking at this. The ranges, you can easily make mistakes. But okay, this is in fact is correct. So let's see. So this must be 0. Okay. Can we prove that? No. Can we see what is the condition? Clearly, there is some relation. It cannot be 0 for all values of j, right? So there must be some relation between j and n. So let's just try to work it out. I can use this here. So let's just open this up. So there's two terms. One is r equal to 0 to L of 2j minus L, and another term I write it as plus 2. This 2 is multiplying everything. 2 times sum over r equal to 0 to L r. This I can pull it out because after all there is no r dependence here. So this expression is simply 2j minus L times r plus 1, because there are r plus L plus 1, because there are L minus 1 terms, right? Including 0, there's L plus 1 terms. And the second one is 2, and this sum, you know this is what it is, L times L plus 1 by 2. Right. sum of R going from 0 to L is L times L plus 1, right? Or equal, also, R equal to 0 doesn't contribute, so it's the same as R equal to 1 to L. That's it. Right? You remember, everyone wants, right? I mean, one way to prove this is called, what is that? That is 1 plus 2 plus 3 plus all the way up to F, right? This is some number. Let's call it Q. We want to compute what is that Q. Now let's rewrite again Q, but now let's change the order. So right, this L plus L minus 1, L minus 2, all the way up to 1. And then just add it up. I mean, so this becomes 2Q. But now you see, just add like this with that, and so on. So that is the same as L plus 1 plus L plus 1, all the way to L plus 1 again, the last one, L plus 1. And there are L terms here, so you get L times L plus 1 divided by 2. I mean, if you don't remember, this is, anyway, this is. So this 2 cancels. So the total, the L plus 1 comes out as a common factor. So this is the answer is L plus 1 times 2j minus 2L plus L. That is the result of the sum. This sum. This sum is the same as that sum. So the total answer is that. So it's L cancels, and that makes it minus L. So this is supposed to be 0. Okay. This has to be 0 because that's our conclusion. Right? If this was the lowest state, then this should be 0. So this L plus 1 cannot be 0 because L is a non-negative number, right? Because L was the number of times you got combined. Of course, L could have been 0, but not minus 1. L could have been 0 means already this state is the lowest state. Is the highest state and the lowest state. But so in general, L is a non-negative integer. It could be 0, 1, 2, 3, but not negative. So this cannot be 0. So only way it can be 0 is that is 0. But this implies that J equal to L by 2. But L is an integer. So this proves that J can be either an integer or a function. Okay? That is it. So that is which you already know from the quantum mechanics. Like not really. In quantum mechanics, you have not done this. In quantum mechanics, you have been doing SO3, not SO2. Right? In SO3, you remember the JT quantum number was always ET. But here we are saying that it is not necessary, it could be also half integer. And we see the difference. This is because we are doing SO2, not SO3. If you were doing SO3, this would not be ET. And we will discuss that, not today, but it's so already. Okay. So I should just finish. So this is one way of doing it. But I just quickly, maybe I just leave this as an exercise. I mean, exercise means just not for submission for the tutorial, but just let's try to work it out today to the evening. You see, there's another way of doing it, where again you get the same answer, but it's much easier, much more direct. I mean, this can be generalized in much more complicated situations. This particular. Now the point here is to look at this equation, this commutation. This commutation relation says that E plus E minus commutator is 2H. I mean, because we would call it R has been replaced by this capital letter. Okay. Now suppose I want to compute the trace of H or 2H, doesn't matter. In this space, space of what? Space of this, what we said, E prime, E minus, E prime, E minus L, phi prime. Right? This was the L plus 1 dimensional space. Because here, L plus 1 dimensional space. So in this space, of course, because we know that this is closed under the action of E plus E minus sign to H and H, meaning E plus takes you state from here and brings it back here. E minus again takes a state and brings it back here. And H again is this eigenfunction. H also brings it back here. This means that E plus, E minus, and H, I can write them as L plus 1 by L plus 1 matrices. Right? Because this is a vector space. I mean, these are the basis vectors. You can write down the L column, L plus 1 column vector. And all of these things, I can write them as matrices. L plus 1 by L plus 1 matrices. Each one, H plus, H, E plus, E minus, and H. That's because it's closed under action. That is why it was so crucial to prove that there are no new states, there are no degenerate states. No, that was the reason. So now, so this is really trace, thinking of this as L plus 1 cross L plus 1 matrix. All of this is, so this, all of these guys, this guy, and this guy, are all L plus 1 cross L plus 1 matrices. And now I'm taking the trace over of H in this L plus 1 dimensional space. Suppose I do that. Alright? Well, this is the same as 1/2 trace E plus E minus commuted on this space, on the same space. But the trace of the commutator is always 0, right? Because after all, this is trace of E plus E minus minus E minus E plus. But it is a cyclic property of the trace. You can move the matrices around, and this vanishes. So then since you know in this L plus 1 dimensional space H is a diagonal matrix, because in this base H is a diagonal matrix with an entries being eigenvalues. So the trace must vanish. Check that this condition gives you the same relation that this is. This way of proceeding is more easily justified. Okay, let's stop.
Professor, I have a question from the first part of the lecture.
From the previous lecture?
No, today's lecture, first part of the lecture.
Okay.
So we talked about the action representation of Lie algebra. So suppose we have a Lie algebra which has bases like E1, E2 up to En.
Okay.
And say we can divide this say into two, like E1 up to say En, and then En plus 1 up to En. And suppose that the two sets are like if you take the commutator between like two elements from the first set, we get something from the first set, and they don't mix up.
Yeah.
So does that imply that in that case our actual representation will be a reducible representation, like from diagonal to the
Exactly. Yeah, correct. Because in that case, essentially there are these subalgebras. There are two subalgebras. You said E1 to some, and then the remaining guys. So they will generate two different subalgebras, and these two subalgebras don't talk to each other; they commute with each other. So this is what we call semi-simple algebras. So SU2 is a simple algebra because there's no such division in two parts. But for example, if you take SO4, you find that this is not a semi-simple algebra. In that case, this happens. Yeah, it will be reducible. A joint representation will be reducible.
And Professor, whenever we have in the algebra, we always have the action representation, right?
Mm-hmm. Yeah.
I mean, it's always possible.
Yeah, that's because
whenever we talk about the algebra, we by default we already have two representations. One of them is the actual representation, and the other one is the dual vector space of the actual representation. And whenever we have a vector space, we always have a dual vector space.
Yeah. No, sure. Yeah, that is fine. But I mean, the representation is essentially the same. There's one adjoint representation, but there are also other representations come for free, which is at least for the matrix algebras. Matrix groups, there's already defining a representation, right? For example, for SU2, the two-dimensional representation already there. It came for free, right? and then the adjoint was three-dimensional. So typically, when we discuss all these matrix algebra, matrix groups, so there is a defining representation, right? And then there is a adjoint representation comes for free, and there is one more representation which comes for free, which is a trivial representation, which is a one-dimensional representation, where you just take all the generators and they act as zero. No? Because the commutator of 0 with 0 is doesn't matter. No? So no matter what the structure constants are, this is always be satisfied. So that's the one-dimensional representation is always there, which is a trivial representation. So the Lie algebra elements are 0, acting in that representation, which means the group it doesn't do anything to that one-dimensional state. It's invariant state. Yeah. But everything else will be.
We can also consider the well vector space of the actual representation. Like for any vector space, we have a well vector space.
True. Yes. Yeah. But it's equivalent representation. It's not. It turns out to be the same representation. Yeah. Okay. So yeah. So then we'll meet tomorrow. Now it's already late. So sorry for taking so much time. Today you must be tired also from the previous lecture. The days when there is only one lecture, okay, I can take more liberties.
One question. All these terms also describe harmony and also this.
Yeah. So I see the relationship a little bit. I will discuss it tomorrow. Yeah, the relationship. It has to do with the fact that this, I told you that in SU2, two elements are mapped to the same element in SU2. The G of SU2 and minus G of SU2 are mapped to the same. So it will turn out that for the half integer space, spin half, J half, 3 half, and so on and so forth, G and minus G are acting as one of them acts as a plus one, another one acts as a minus one. But in SO3, they should be acting both as one. Right? So in SO3, you can't have representations. So only integer representations in SO3. But really, we are the same, SO3 or SO2 is the same. When we say that SO3 only the integers appear, then we are really talking about the full global loop, not just the infinitesimal information. So when you talk about the full loop, then half integers is going to be Okay, so by then, see you tomorrow.